everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about a very important equation in quantum mechanics, that is time-independent Schrodinger wave equation. Let us look at the brief outline of the topics we have discussed thus far. We have seen the introduction to quantum physics, then de Broglie hypothesis, the wave-particle duality, and then in the last lecture we have discussed about the Davison and Germer experiment. Now, while deriving the time-independent Schrodinger wave equation, we are going to use all these concepts. Whatever we have discussed thus far, we will be using them to derive this time-independent Schrodinger wave equation. Now, how we are going to go about this topic? First, we will see quickly about the development of quantum theory, how quantum theory has developed, and then we will talk about the wave function and then derive the equation, that is the Schrodinger wave equation. So, if you see the background of this equation, till 19th century, light was thought to consist of waves of electromagnetic fields which propagated according to Maxwell's equations, while matter was thought to consist of localized particles. This is the classical theory, classical according to classical mechanics. What they believed, according to classical mechanics, they believed that light consists of only waves, means it exhibits only wave nature, and it propagates in the form of electromagnetic fields, and they can be expressed with the help of Maxwell's equations. So whenever they have to talk about light or show the propagation of light, they took the help of some equations which we call them as Maxwell's equations. And when it comes to matter, they thought matter should always be localized as particles. This is according to classical mechanics. But this division, that is light acting as a wave and matter having particle nature, this division was exposed to doubt. This was exposed to doubt when Planck gave his black body radiation theory. He did an experiment using the black body and he proposed that radiation is emitted in discrete quanta, because when we are talking about classical mechanics, they always considered that energy is continuous. It is continuous in nature. But Planck proposed that radiation is emitted in discrete quanta. Discrete means in steps or in small packets of energy. Let us see what Planck has put forward. Planck's theory explained the energy spectrum very well with the help of black body radiation, and it introduced a new concept. What is a new concept? Energy is absorbed or emitted in discrete manner. It is no more continuous. As per classical mechanics, they considered it to be continuous. But with this black body radiation, with this experiment, he could show that energy is absorbed as well as emitted in discrete manner in terms of quanta. Quanta here is nothing but a packet of energy, and the energy of each packet is given by E is equal to h nu. That is why we are talking about magnitude h nu. So E here is the energy of photon is an integral multiple of h nu, we can say. So E is equal to n h nu, where n can take on the values 0, 1, 2, 3 and so on. H is Planck's constant. And nu is frequency of radiation. So when the value of n is taken as discrete, either 0, 1, 2, 3 and so on. If it is 0 means there is no energy emitted. So we may consider from 1, 2, 3 and so on. So when it is discrete, so the energy is also emitted in discrete packets, which we are calling them as quanta. Now what are the conclusions given by Planck's theory? Black body radiation is a characteristic of temperature. He said it depends upon the temperature. How it depends upon the temperature? When the black body is at a higher temperature than the surroundings, it emitted radiation. And when it is at a lower temperature or when energy is incident on it, it absorbed the radiation. And always the emission is more than the absorption at higher temperatures. So he said that it is a characteristic of temperature. Then black body radiation also proved the quantized nature of light. Till then nobody agreed that light could be in the form of small packets, or it can be discrete, or it can be quantized. Quantized means in small packets and not continuous. So black body radiation, I can say, will be the first experiment to prove the quantized nature of light. Now, in the year 1905, Albert Einstein extended the Planck's hypothesis to photoelectric effect. So he was doing an experiment, photoelectric effect. What is photoelectric effect? It is the emission of electrons from the surface of a metal when light of suitable frequency is incident on it. So what we are seeing here is, if you have a metal surface and when light of suitable frequency, this is the light that is incident on the metal surface. If this light is of suitable frequency, then electrons can be emitted. So when I'm talking about suitable frequency, I can calculate the energy because energy is proportional to frequency. So actually this was given by Planck. So Einstein used the Planck's hypothesis to explain his photoelectric effect. He talked in terms of photons, because when this light is incident on the metal surface, whenever there is an interaction of radiation with matter, you will have to consider it in discrete or the particle nature of light. So he used the Planck's theory to explain the photoelectric effect. What did he say? The beam of light is really a stream of particles. He said it is not falling on the metal plate continuously. If this is the metal plate that is taken, if light is incident on it, it is not continuous. It is like shooting off photons onto the metal surface. So this is the concept he has used. Beam of light is actually a stream of particles. And these particles are called photons. So what is a photon? A photon is nothing but a packet of energy. So now we can say that light is incident on the metal surface in the form of photons. Then each photon possesses the energy given by the equation E is equal to h nu or E is equal to n h nu. This study of photoelectric effect by Einstein, it has helped physicists to understand the quantum nature of light and electrons. So then he also calculated and has given the equations regarding what is the amount of light that is incident on the metal plate, and he could also calculate the energy of the emitted electrons. So this led to the concept of wave-particle duality. So he proved, this photoelectric effect also helped scientists to understand the quantum nature of light as well as electrons. So this led to the concept of wave-particle duality. We have discussed in detail about wave-particle duality. Wave-particle duality, why we are telling, we will not restrict our understanding of light only to a wave or to a particle, because under certain circumstances we use the wave nature of light to explain the propagation or to explain certain phenomena like interference and diffraction. But here we use the particle nature. Whenever we are talking about the black body radiation or again the photoelectric effect, all these are proving the particle nature. So they said it should have a dual nature. I will say it is dual nature. Dual means it has both wave as well as particle nature. So in this view, how do we define light? Light is considered to be as a collection of one or more photons propagating through space as electromagnetic waves. So they are combining both. So initially the classical physicists said it travels only in the form of electromagnetic waves. So now how did they incorporate the dual nature? They said it is a collection of photons and propagating through space as electromagnetic waves. Then comes the scientist Compton. He also contributed in understanding the particle nature of light. Actually, he was doing experiments with X-rays and he was calculating the scattering phenomena. Then he observed the shift in wavelengths after being incident on a metal plate. The radiation that is reflected is undergoing a shift in wavelength. While studying it and it helped to understand the wave nature or as well as the particle nature of light. So what Compton did is he used the Einstein idea of light as a particle. So Compton has a very important place in the history of physics because it shows that electromagnetic radiation cannot be explained as a purely wave phenomena. Means if you consider the radiation only as a wave, you cannot explain many things, many phenomena, many other phenomena. So this Compton effect also helped in understanding the quantum nature or the particle nature of radiation. Then comes the scientist Niels Bohr. A major contribution was made by Niels Bohr, who applied the quantum hypothesis to atomic spectra. So he was studying about the structure of atom and how the electrons or the subatomic particles revolve or move in a atom. Then when he was studying about the energies related to that, he found that radiation from gaseous atoms at low pressure consisted of a set of discrete wavelengths. So till then it was considered wavelength to be continuous. But when he found out with the help of these gaseous atoms at low pressure, it consisted of a set of discrete. Discrete means again here not continuous. The wavelengths were not continuous. So what we understand here is, first classical mechanics. We had classical physicists who said that light propagates as electromagnetic waves and it is continuous in nature. But then came the black body radiation by Planck. He said light is emitted or absorbed in the form of small packets called quanta. And then we have the photoelectric effect by Einstein, where Einstein used the Planck's theory. The Planck's theory put forward by Planck was used by Einstein to explain the interaction of radiation with the metal atoms. And after that, there is this scientist Compton, who gave the Compton effect. He also contributed to understand the quantum nature of light. And then the Neil Bohr studies about the atomic spectra. So all these helped in understanding the quantum nature, and they concluded that it has dual nature. Just not wave or particle, but it has both wave as well as particle nature. This is the background. Okay, now using this, another scientist by name de Broglie, he gave a very radical hypothesis. What he said was, if light can act like a wave sometimes and like a particle at other times, then all matter, usually thought of as particles, should exhibit wave-like behavior. So when he has seen all these developments, no, and then they also have concluded that it should have dual nature. So what he suggested is, if light can act like a wave sometimes and particle at sometimes, then matter, which is a particle, which is thought of to be like a particle, should also exhibit wave-like behavior. It is just his logical thinking, because he said the reason could be because everything in nature is symmetric. So this also should follow the symmetric principle. So what he said is, since radiation has been shown to possess dual nature, matter must also possess dual nature. So the next step, what he said, after all this we have concluded that light has dual nature. So matter also must possess dual nature. Now what we have done, radiation is supplemented with particle characteristics to explain certain optical phenomena such as photoelectric effect. So to consider or to explain the photoelectric effect, I told you Einstein used the concept of Planck's theory, okay, where he considered it as particle. And similar lines, material particles also have to be supplemented with wave aspect. When radiation could be supplemented with particle characteristics, then his thought was material particles also can be supplemented with wave aspect for the full understanding of their behavior. This is what de Broglie proposed. Now, to make his theory further stronger, he proposed a relationship between the momentum of the particle with the wavelength. Why he had to derive a relationship between momentum and wavelength is, momentum is a parameter which is always associated with particle. Whenever we talk about particle, it has a mass, it has velocity, then we can express it in terms of momentum. Whenever we talk about wave, we talk in terms of wavelength. Now, if he could establish a relationship between momentum of the particle and the wavelength, then whatever he proposed proved to be correct. Then the de Broglie equation is one of the equations that is commonly used to define the wave properties of matter. Then what he said is, when we are talking about this particle exhibiting wave nature, they are called as matter waves. He called them as a different type of waves, because for light we are talking as electromagnetic radiation, but here for matter we are calling them as matter waves. And he derived a relationship between the two, and that is the famous relationship lambda is equal to h upon p. Lambda is the wavelength, where we talk about a wave in terms of wavelength. H is the Planck's constant and p is the momentum. So with the help of this relationship, he could establish a relationship between wavelength, that is the wave nature, and momentum, that is the particle nature. Now, the significance of this de Broglie relationship is that it is more useful to microscopic fundamental particles like electron. Even though he said it could be applied to macroscopic particles also, but It proved to be very successful because classical mechanics failed to explain the microscopic behavior of particles, of the fundamental particles like electrons. When we consider the fundamental particles, protons, electrons and neutrons, and they are microscopic in nature, quantum physics or quantum theory could not explain the microscopic phenomena. So de Broglie relationship was very useful, and it gained lot of importance because it could be applied to microscopic fundamental particles like electrons. Now coming to the equation. At the beginning of the 20th century, experimental evidence suggested that atomic particles were also wave-like in nature. We also have seen the Davison and Germer experiment. Davison and Germer are two scientists. Actually, they were working with crystal studies. They were trying to study the surface of the crystal and its nature. But when they have encountered that electrons were undergoing diffraction patterns or showing diffraction patterns, then they said that electrons can exhibit wave-like nature. And they could prove with the help of the Davison-Germer experiment, they could show that the experimental values, they did the experiments with different voltages and at different angles of incidence and calculated the value using experiment, and they compared the results with the theoretical results which we get from Bragg's law. So when they have compared, both of them found to be matching or approximately equal. So that proved that these electrons exhibit wave nature. So there was experimental evidence also, and later on there were other scientists also who did experiments to prove the wave-like nature. But Davison and Germer's experiment was the first experiment to show the wave-like nature of electrons. Now, as I explained, electrons were found to give diffraction patterns when passed through a double slit in a similar way to light waves, because till then it was an established fact that light waves undergo diffraction. What is diffraction? It is nothing but the bending of the light around the corners of the obstacle. Means when light falls on an obstacle, and if the size of the obstacle is very small, of the order of the wavelength of light that is incident on it, then it undergoes diffraction, that is bending. Now, when these electrons are also showing diffraction patterns, they said that it should possess wave nature. So, therefore, it was reasonable to assume that a wave equation could explain the behavior of atomic particles. Now, when we want to show the wave nature, like I told you, if we have to explain or talk about light radiation or the propagation, we were using the Maxwell's equations to explain about the light radiation or to talk about the propagation of light radiation. Now, when we are considering electrons exhibiting wave nature, then to talk about the wave nature, you need an equation, a wave equation, which can help the wave nature of particles. Now, wave equations are normally derived from other physical laws. Okay, the wave equation for mechanical vibrations on strings and in matter could be derived from Newton's laws. Whenever they want to show a wave, they were using the wave equations. Or here, if you are talking about the vibrations in a string, when the particles of a string vibrate, and these vibrations give rise to waves. And when the wave propagates, you need a wave equation to explain that. And those equations are derived from the basic laws, that is the Newton's laws of motion. Now, in electromagnetic waves, from Maxwell's equations, the wave functions are electric and magnetic fields. No? Because when we are talking about the radiation and the Maxwell's equations, we talked in terms of electromagnetic waves. So, to denote these electromagnetic waves, what are the wave functions we have used? They are the electric and the magnetic fields. But now when we are talking about the wave nature of electrons, we are talking in terms of matter waves, I told you. They are matter waves. Now, Schrodinger wave equation is a mathematical expression describing the energy and position of the electron in space and time. Okay, so now I told you we need an equation to express this wave nature. So, Schrodinger equation is a mathematical expression which describes what it describes: the energy and the position of the electron in space and time. If you have to find where the particle is at a particular time in space, and if you have to talk about the energy and its position, then you need an equation. Okay, and here we have to take into account the wave nature of the electron. So wave nature of the electron inside an atom, because why we are talking about atom? When you talk about electrons, you should go back to the structure of atom, where in an atom you have the nucleus at the center and electrons revolving round the nucleus. Now, until Niels Bohr established the fact that they can be only in orbits whose angular momentum is an integral multiple of h by 2 pi, they considered it to be continuous. But after this quantum theory, they accepted that these electrons will be in fixed stationary orbits and they will have the energy related or to that orbit only. They cannot have energy in a continuous manner. So that is why they have to consider the wave nature of electron inside an atom. Because when we are talking about these electrons, we have already discussed in matter waves the properties of matter waves. These electrons which are moving, only moving electrons, exhibit wave nature. If the velocity of the particle is zero, because we have seen this relation, de Broglie gave the relation lambda is equal to h by p, where p is the momentum, so we write h upon mv. If the velocity of the particle is zero, the lambda becomes infinite, which is not possible. So only moving particles, if v is equal to 0, it will not exhibit wave nature. So what we are talking about here is about moving particles. Now, because these electrons are moving in their orbits, they are exhibiting the wave nature. And to derive the Schrodinger wave equation, he made three basic considerations. What are the considerations he made were, he considered a classical plane wave equation, because even in classical mechanics, if you have to describe a wave, you need a wave equation. So generally what we do in classical mechanics is you always represent the displacement of the particle by y is equal to a sine omega t minus kx. So this is a basic classical plane wave equation. So y is the displacement. A here represents the amplitude of the wave, and we are talking about a sinusoidal wave function. So omega is the angular velocity, t is the time, k is the wave vector, and x is the displacement. So we are talking in terms of space as well as time. So we are mentioned here, whenever we are talking about a wave, you have to specify what position it is at what time. So the variation of the position of the particle with respect to time. So we have to consider the basic equation, that is the classical plane wave equation, and then we will apply the de Broglie hypothesis of matter wave. How did he explain the relationship between the momentum of the particle and the wavelength of wave? So into this equation, we will have to incorporate the de Broglie hypothesis. And then we also have to consider the conservation of energy. We cannot neglect this concept of conservation of energy. Means energy can neither be created nor destroyed. It can only be converted, or it can only be converted from one form to the other form. So the basic equation we take here is total energy is always equal to the potential energy plus kinetic energy. Total energy is equal to potential energy plus kinetic energy. This is what we call in terms of in mechanical vibrations when we are talking about. So we are going to consider all these three considerations while deriving the Schrodinger wave equation. Now this equation, that is the Schrodinger equation, gives us a detailed account of the form of wave functions or the probability waves that control the motion of smaller particles. So here what we are doing, we are talking about particles. We are talking about the elementary particles like electrons, protons and neutrons. So it is giving us the detailed information about the wave function, which helps in understanding the motion of smaller here we are talking about microscopic particles. And not only that, this equation also describes how these waves are influenced by external factors, be it the variation in mass and velocity or the forces that are acting on them. So this equation helps to understand the influence of the external factors also. Now, this equation also makes use of the energy conservation concept that offers about the details about the behavior of electron that is attached to the nucleus. So when we are talking about energy conservation, I said energy can neither be lost nor added. So in order to understand the movement of electrons, so movement of electrons, how can the electrons move? They said if the electrons, this is the nucleus, you have the electrons revolving in fixed orbit. This is one, and you may have electrons here. Now, when an electron jumps from here to here or comes from a higher level to lower level, if I say this is E1 and this is E2, because it is coming from higher level to lower level, the difference in energy has to be emitted. So, energy emitted E, if you say in terms of h nu, this should be here equal to E2 minus E1. Or if an electron has to go from a lower level to a higher level, from E1 to E2, if it has to come from here to here, so definitely E2 is at a higher level than E1. So you need to supply energy to this electron, which is equal to the difference in energy between the two levels. The difference in energy has to be supplied to this electron for it to go into the higher orbit. So here also the energy conservation is taken care of. So it also gives us the details about the behavior of an electron that is attached to the nucleus. Now Schrodinger is the first person to write down such an equation. Other scientists did not have any clue what the equation meant, but they only knew that we need an equation if you have to talk about matter waves. If you have to express or see the propagation of these waves, we need wave equations. And then the eigenvalues of the wave equation. Eigenvalues means when you are solving this equation, you get the solutions and they give us the eigenvalues. Eigenvalues are nothing but energy values. They are shown to be equal to the energy levels of the quantum mechanical system. So what the solutions to the wave equations are giving us the eigenvalues and also the eigenfunctions. Then these eigenvalues are equal to the energy levels of the quantum mechanical system. Now the best test of the equation, because when he said that this is the equation and this helps us to understand about the energy levels and we can also get the energy levels, then he had to prove it. So what he did was he applied it to the energy levels of hydrogen atom, the simplest atom. Okay, so he has taken and tried to apply it for the hydrogen atom. And the energy levels were found to be in accordance with the Rydberg's law. You know the Rydberg's law. So he gave a relationship between the energy levels, no, of n is equal to quantum number, n is equal to 1, 2, 3 and so on, how these energy levels vary, the energy varies. So whatever equation we are talking about here is giving us the energy values which are perfectly matching with the energy levels that was given by Rydberg's law. Now, Schrodinger wave equation shows all the wave-like properties of matter, and it was one of the greatest achievements of the 20th century science. So, unless he could give an equation once you get, you can find all the other details about the quantum mechanical system. And then it was used to find the energy levels of quantum mechanical systems. So it is the other way around. Now we know where the electrons exist, what is there in an atom, what are the energy levels. But before the invention, because this equation was there, and with the help of the solutions that were given by this equation, they could clearly tell about the energy levels of quantum mechanical system. That is why it has become a very important and the greatest achievement in the 20th century, because it could be applied to atoms, transistors and so on. Now the solution to this equation is a wave that describes all the quantum aspects of the system. And the associated wave function, what is a wave function that is associated with this equation, will give us the probability of finding the particle. Because when we were talking about the wave nature, in the beginning we said, if you talk about a particle means it is localized. It is localized in space. You can talk about the exact position of the particle. But when we talk in terms of a wave, you cannot tell its exact position. Okay. So this wave function solved this problem of locating the particle. So it is talking in terms of the probability. So what is the probability of finding the particle in this wave at this position or any other position, at a certain position? So the wave function will help us. No? It gives us the probability of finding the particle at a certain position. Now, when we are talking about this Schrodinger wave equation, there are two types. In Schrodinger wave equation, we have the time-dependent equation, time-dependent, and time-independent. So, two forms. Here in time-independent means we will consider it as a function of position as well as time. Here, when we are talking about t, we will consider it to be a constant. So, that is the time-independent. So, the time-dependent equation is used for progressive waves whenever we are talking about progressive waves. Progressive waves are waves that travel forward into the medium and will never return back. They just propagate forward. They are called progressive waves. So we use the time-dependent equation to describe the progressive waves. And the time-independent form, where we will not consider the variation of time, we will use to describe the standing waves. What are standing waves? How are standing waves formed? If you are talking about the vibrations in a stretched string, if I have a wave which is moving forward in a medium, which is obstructed, okay, then the wave will get reflected back. If this is the wave in the forward direction, this is the reflected wave. And in standing waves, the main thing is the energy is limited to this region. Energy is not propagated forward. Energy is limited to this region, and it is caused due to the superposition of waves. Okay, so the time independent form is used to describe the standing waves. So in this topic, in this class, we are going to discuss only about the time-independent Schrodinger wave equation. We are not going to derive the time-dependent equation. Maybe in some other class, we will be touching upon the time-dependent equation. Now, to derive the equation, to understand how to derive the equation, we will start and try to understand with something we know. We already know the Newton's laws of motion. I told you, which we use for classical mechanical systems. So what is the equation we use to describe the motion of a particle in classical mechanics? We generally use the equation from Newton's second law, which gives us F is equal to ma. What is the Newton's second law? It relates the rate of change of momentum is always proportional to the force that is applied on the particle. So the rate of change of momentum is proportional to the force. So from that we get F is equal to ma. So what F is equal to ma described here is, this is the force, this is the fundamental equation here, m is the mass, and this is the acceleration. So this is used to make the mathematical prediction as to what path a physical system will take over following a set of initial conditions. So we have been using this equation to trace the path of a particle or to predict where the particle will be with a set of initial conditions. What is the force applied? What is the mass? So depending upon these two, what will be the acceleration of the particle? So we can predict very easily. So solving this equation will give us the position of the particle. It also gives us about the momentum, information about the momentum of the system, and it is a function of the external force. So what is happening here? More the force applied, more the acceleration, maybe if the mass is kept constant. So what it describes is, it describes the position as well as momentum as a function of external force that is applied. And these two parameters are sufficient to describe the state at any point of time, at any instant. You need these two parameters, that is the position and the momentum. So in quantum mechanics, the analog of Newton's law is Schrodinger equation. Now, because the Schrodinger equation is a new equation, you should not get confused. So once you are getting clear of the idea of Newton's law, where we are using Newton's law, how we are using, how it is applied to understand the position as well as the momentum of a particle, the same way we will use the Schrodinger wave equation to understand the behavior of the particle as a wave. Now, solutions to the Schrodinger equation describe not only molecular, atomic and subatomic systems, but also macroscopic systems, possibly even the whole universe. Now, when I told you where classical mechanics failed is, classical mechanics failed to explain the microscopic systems, then we had the quantum mechanics, which could successfully explain the microscopic system. But not only that, the greatest advantage of this is it could also be extended to macroscopic systems. So at one point of time, when the size of the objects increases, so the quantum mechanics slowly, it also is successful in explaining the macroscopic system. So possibly the whole universe, they say. So the foundation of this equation is structured on a linear differential equation that is based on classical energy conservation and consistent with de Broglie equation. I told you. So what it did, why we are trying to find out or derive an equation, what is the importance and what is the need for it, we have discussed. No? And how we are going to derive this equation also we have seen. So now when we have to derive this equation, so he developed the differential equation whose solutions yield possible wave functions. So when you are deriving the differential equation, you get the wave functions that are associated with the particle. And this equation will tell us how the wave equation changes as a result of forces. So the same way we have done in classical mechanics, here also, if there are any external forces, okay, that are acting on the particle, how does the wave function vary? That could also be very easily derived. Now, considering the de Broglie's equation. So, how did we get the de Broglie equation? First, we have considered the Einstein's equation, that is the Planck's quantum theory, E is equal to h nu. And then de Broglie gave us this relation P is equal to h upon lambda. Okay, so we are going to use these two equations. This is the, according to the Planck's hypothesis, we have E is equal to h nu. And according to de Broglie hypothesis, we have P is equal to h by lambda. Now we are going to derive this equation. How? In terms of a definite path. What quantum mechanics acknowledges is the wave-particle duality of matter. After de Broglie, they started accepting that even particles or matter will exhibit dual nature, that is wave-particle duality. Then, rather than traveling along a definite path, a particle is distributed through space like a wave. Because when I talk about particle, it will have a definite path. But when I talk about a wave, it will vary in space. And the wave in quantum mechanics replaces the concept of particle trajectory and is called the wave function. So when we are talking in classical mechanics, we are talking about the path of the particle or the particle trajectory. But in quantum mechanics, we talk in terms of wave function, which is denoted by a Greek alphabet psi. Actually, you write it as PSI. P is silent here, so we call it as psi. So the wave function is always denoted by psi. Rather than saying that the particle has a specified position and momentum, we describe it by a wave function, which is a function of all the coordinates of the particle and of the time. Means, no more we are considering it as a particle. So we'll have to consider it as a function, or the wave function. It is a function of all the coordinates. We are considering all the in 3 dimensions when you consider. If you are considering it in 1 dimension, we will talk only in terms of position and time, the position coordinate given by x and the time given by t. But when it comes to 3 dimensions, we write it in terms of x, y, z and t. Now we are going to derive this. You are considering a particle of mass m, which is moving with a velocity v and associated with a group of waves of wave velocity omega and wave function psi. So we are talking about the particle. Its mass is m, its velocity is v, and because we are talking about the wave nature of this particle, the wave velocity is given by omega, and to represent it we are using a wave function psi. Now, as we have discussed the 3 steps, we are following the 3 steps. First, we'll use the classical plane equation. So, let us consider the simple form of wave expression. What is a simple form of wave expression? Psi. The simple form of wave expression is psi is equal to psi naught sine omega t minus kx. Now, I told you the wave function here is represented in terms of psi. So, psi is given by psi naught. Psi naught here represents the amplitude. Okay. Omega we have described, it is the wave velocity, t is the time, k is the wave vector, x is the displacement. Now, once you have psi, you can find dou psi by dou x, taking the derivative of psi with respect to x. And I told you we are deriving the time independent equation. We are keeping the time constant here. Time is constant. So, dou psi by dou x will be equal to what? Psi naught. Here we will have to go back to our basic formula of differentiation. D by dx of sine x will be equal to cos x. Okay. And if you have d by dx of sine 2x, it will be cos 2x, and then d by dx of 2x will be 2. Now same basic formula we are going to use here. So if I have to take the derivative of psi with respect to x, I have psi naught here, and the derivative of sine omega t minus kx is cos omega t minus kx, and I'm keeping time constant, time independent. So for kx, we'll get, here it is minus, so you will have a minus k cos omega t minus kx. Then take the second derivative, dou square psi by dou x square will be equal to minus psi naught k square. Why k square? Because for cos omega t minus kx, you get sine minus sine omega t minus kx, and for minus kx, you will get minus k. So what we are going to get here, minus into minus plus k sine omega t minus kx. So we already have a minus k. So minus k into k will give us minus k square. So minus sine naught k square sine omega t minus kx. I will simply rearrange these terms and write it as, I will write it as minus k square sine naught into sine omega t minus kx. Minus k square into sine naught sine omega t minus kx. What is sine naught sine omega t minus kx? It is nothing but psi. Psi is equal to sine naught sine omega t minus kx. So for this, I can substitute psi. So what we get? Dou square psi by dou x square is equal to minus k square psi. So this is the first step where we are considering the plane equation. Now coming to incorporating the de Broglie hypothesis. So here I said the wave vector k is equal to 2 pi by lambda. So what we are doing here? Incorporate de Broglie hypothesis or de Broglie relation in the second step. So k is equal to 2 pi by lambda, and what is lambda? The relationship between lambda and momentum is given by h by p, and p is equal to mv. So if for k, I substitute for lambda h by p, or if I write k is equal to 2 pi by lambda, and we have seen that lambda is equal to h by p, and p is equal to mv, which is nothing but momentum. So if I rearrange it and write it, we get k is equal to 2 pi mv upon h. So this is what we get. K is equal to 2 pi mv upon h. In the equation, what we need is k square. So if you want k square, you will simply square on both the sides. So k square will give us what? Squaring on both sides. 4 pi square m square v square upon h square. So that is what we are going to use now to write this equation. So substitute this value of k square in this equation. Maybe I'll write this as equation 1. Substitute the value of k square here. So dou square psi by dou x square is equal to minus, because we have a minus here. For k square, we will substitute 4 pi square m square v square by h square psi. Now 4 is a constant, pi is a constant, h is a Planck's constant. All these are constant. So instead of so many constants, we can write one constant using the relation h cross is equal to h upon 2 pi. So what will be h cross square? H square upon 4 pi square. So here in place of 4 pi square upon h square, I will substitute 1 upon h cross square. You got it? H cross is equal to h upon 2 pi. We are trying to replace two constants with only one constant, that is h cross. And h cross square is what? H square upon 4 pi square. But in the equation, we need the value of 4 pi square by h square. So what we get here is 1 upon h cross square. So substitute for h cross square here. Dou square psi by dou x square is equal to minus. We have m square v square in the numerator, and we are going to write h cross square psi. Take this on to the other side. If you are taking this term onto the other side, you get an equation. Dou square psi by dou x square plus m square v square by h cross square psi is equal to 0. This is the equation which you will have to take forward. So in the second step, we have incorporated the de Broglie relation. Now, the third step. In the third step, what we are going to see here is the conservation of energy. The third step is to see that the energy is conserved throughout. So, the total energy is the sum of kinetic energy K and the potential energy. So, here E represents the total energy, K is the kinetic energy, and V is the potential energy. So, we are representing it as K, E is equal to K plus V. And what is K here? K is nothing but the kinetic energy. The kinetic energy is given by half mv square, because when we are talking about the particle, the mass of the particle is given by m and the velocity is given by v. So the kinetic energy you can easily calculate using the formula half mv square. So now E here always represents the total energy. So the total energy is equal to kinetic energy half mv square plus V. I'll be taking this V onto the other side and write, because we have E is equal to half mv square. This is the kinetic energy plus potential energy. I can take V onto the other side. I'll write it as E minus V is equal to half mv square. I can take this 2 also onto the other side. I can write 2 into E minus V is equal to mv square. Now, you can multiply on both sides. Multiply on both sides with m. Why? I'll explain. On both sides with m. Because if you see the equation here, we had the equation dou square psi by dou x square plus m square v square upon h square psi is equal to 0. This is what we have derived till now. So we want the value of m square v square here. So from this energy conservation principle, I am trying to get the value of m square v square. So if I multiply on both sides, what do I get? 2m into E minus V is equal to m square v square. So for m square v square in this equation, I will substitute 2m into E minus V. So dou square psi by dou x square plus 2m into E minus V by h cross square psi is equal to 0. So that is what we are getting here. Dou square psi by dou x square plus 2m into E minus V by h cross square into psi is equal to 0. So this is the expression we get for the Schrodinger equation. This is the famous time-independent Schrodinger wave equation. So we are trying to write the same equation. From this, how do we write the equation for energy? So since here, I'll try to explain this. We will take the equation dou square psi by dou x square plus 2m into E minus V upon h cross square into psi is equal to 0. Now from this is the equation, time independent Schrodinger wave equation. And you know all the terms. Psi is the wave function, m is the mass, E is the energy. Here when I am talking about energy, it is the total energy. V the potential, h cross is a constant given by h by 2 pi. Now I want to write the formula or the equation for energy. So how do I write? I can take this term onto the other side. 2m into E minus V by h cross square psi. When I'm talking about psi here, it is a function of x. No, that is why we are taking the derivative with respect to x. So dou square psi upon dou x square. I've brought it this side, so I have a minus. Now I want E. So I will take 2m and h cross square also onto the other side. So E minus V psi of x will be equal to minus h cross square by 2m into dou square psi upon dou x square. Now we will take the potential V also onto the other side. Here I'll split it and write E as a function of psi of x minus V is equal to minus h cross square by 2m into dou square psi upon dou x square. I can write now E simply as this minus V. If it comes onto the other side, it will become V psi of x minus h cross square by 2m into dou square psi upon dou x. So this gives the total energy. If you know the equation, Schrodinger equation, you can also get the expression for the energy, which is given by V psi of x minus h cross square by 2m into dou square psi by dou x square. Now for simplicity, we have considered only one dimension. Whatever equation we have considered only in one dimension. But in actual, it may not be a one-dimensional wave. It can be a three-dimensional, because when we are talking about electron that is moving in an atom, it is definitely in three dimension. So we should be able to extend this expression, the Schrodinger wave equation, to three dimensions. So how do we extend it? We are going to now take the derivative with respect to the y and also the z. Because when I talk three dimensions, x, y and z. Now I have taken along the x-axis. Then I have derived only in terms of x. Now I have to extend it or express its position with respect to the x-coordinate, y-coordinate and also the z-coordinate. So I'll write it as dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square with all the three plus 2m into E minus V by h cross square psi is equal to 0. So this is the equation which we have in three dimension. Now where psi is accommodating all the three coordinates here, if you see x, y and z. Now instead of writing the equation all the time in three dimensions, a scientist by name Laplace, he gave an operator which we call it as a Laplacian operator or del square, which accommodates all the three coordinates. So del square is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z. So instead of all this, we will write only del square. So this equation can simply be written as del square psi plus 2m by into E minus V by h cross square psi is equal to 0. So because we are using this, you can simply write in three dimensions the equation as del square psi plus 2m into E minus V by h cross square psi is equal to 0 using the Laplacian operator. Now, what are the solutions to these equations? How do you see this solution? In classical mechanics, if you are talking in classical mechanics, a harmonic oscillator. What do you mean by harmonic oscillator? Harmonic motion means which is a periodic motion, a to and fro motion. Now I consider this particle which is moving to and fro. So in classical mechanics, if I have to represent the vibration of this particle, this is how I can represent A and B. So the harmonic oscillator in classical mechanics can be represented by these two diagrams, A and B. You can see here how it can be represented. Now, in quantum mechanics, where we are talking about this particle will exhibit wave nature, and we have derived an equation for that. Now, if we try to solve that equation, we get 6 solutions. And if you plot the solutions here on the graph, what are the waveforms you get here is C, D, E, F and G, H. All these are the solutions. You can see the waveforms, different waveforms. How we are plotting it? You are taking along the x-axis. So this is the x-axis. You are taking the position. This is the x-axis. And along the y-axis, you are taking the wave function. How the wave function varies with position. That is what we are plotting. So what you are seeing here, you are also seeing two types here. One is the blue one, which always represents the real part. Now, when we talk about the wave function psi, it will always have a real part as well as an imaginary part. It is always represented as, because psi is equal to A plus IB. This is the real part and this is the imaginary part. So when you see here, the blue vertical axis, the real part is denoted by the blue wave and the imaginary part is denoted by the red wave. So whatever we have seen in classical mechanics, the motion of the particle, how it is varying, how do you represent it in quantum mechanics with the help of the solutions that are given by Schrodinger wave equation. So what we try to understand here is, the Schrodinger wave equation is not the only way we study quantum mechanics and make predictions. There are other formulations also, so which were very important. That is, the formulations are which include matrix mechanics, which was introduced by Werner Heisenberg, and also the path integral formulation, which was developed by Richard Feynman. These two scientists also have contributed a lot in taking this equations forward. And then came another scientist, Paul Dirac, who incorporated the matrix mechanics also and the Schrodinger wave equation into a single formulation without seeing them separately. You can talk about the matrix mechanics with the help of Schrodinger equation. Both he has put into a single. They are the Pauli-Dirac formula, which we'll be using in our later lectures. And then if you want to know more about, you can also look at these equations that are given by Feynman and also Heisenberg, and then the Pauli-Dirac equations, which are incorporating both matrix mechanics and Schrodinger equation. For more information, you can refer to these books by Palanitswamy, Garin Gupta, and also Dr. Vijay Kumar. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.